No more than one load per line, right? Everybody understand that one? The loads can be connected in parallel. Loads go on the right. Control devices go between L1 and the load. The load goes between the control devices and L2. The only thing that's allowed between the load and L2 is if we have a magnetic motor starter that with overloads. So the only thing that's allowed is overload contact for magnetic motor starters. Loads can be connected in parallel. How many loads? One load per line, multiple loads per rung. All right, y'all understand the difference? Because in PLCs, it's a little different. Magnetic motor starters. These are relays that are designed to run motors that require external overloads. Like I was telling you in class, some motors have internal overloads. They're inside the motor, and I passed the stator around so y'all could look and see the little overload in there, right? A lot of your industrial motors are designed to run no more than one voltage. And so the overloads have to be designed to sense a certain current. So if I've got a 5 horsepower motor, if I run it at 440, wired to run at 440, it would draw less current than if I wired it to run it to 240, right? You understand that? Yes or no? And why is that? Because it's a 5 horsepower motor. How many watts per horsepower? Anybody remember? Of course, we're still dealing with horsepower, so we got to calculate it. All the other world is given to them, right? You understand? But we have to calculate it. So about how many watts per horsepower? 746 watts per horsepower. So all the rest of the world rates motors in kilowatts. We still rate motors in horsepower, and we got to calculate kilowatts, right? You understand that? And then, of course, I is equal to P over V. So if I've got a 5 horsepower motor, I would take 5 and multiply it by 746. Well, if I divide that by 440, I would come up with a smaller answer than I divide it by 240. And this gets people confused because in DC you learn as the load goes up, if the voltage to a circuit goes up, the current goes up. But what we're doing is we're literally changing the resistance of the motor. So you wire a motor to run these multi-voltage motors, you literally have to rewire the motor to run at a different voltage. And when you do that, you change the value of R, right? You understand? So basically, so that means this is why we have these external overloads, is that if I rewire the motor for a higher voltage, then I've got to change the overload. The overload sensors, not the overloads themselves. So that's the only thing that's allowed between L1 and between the load and L2 is the overloads that's required by a magnetic motor starter. And we've already talked about that. How we control devices does not determine if the circuit is a series parallel circuit. So we can hook control devices in series, we can hook control devices in parallel, we can hook control devices in series parallel. What determines the load is over here, right, on the right hand side. Line numbers go on the left. A line number is different from a rung number. So in motor controls, we deal with line numbers. Every horizontal line gets a line number if it's drawn correctly. Everybody understand that? Yes or no? If you don't put dots on the L1 and L2 side, what does that mean? It's not connected. Everybody okay? So we start line numbers on the left-hand side and you just come straight down. Contacts. So relays have contacts, right? You understand that. We call them contacts. These are the switches that's being controlled by the coil of the relay. So what we do to make the print easier to read is we put the location of a relay's contact on the right-hand side of L2 on the same line that the actual coil's on. So when I see this guy CR1 right here, then I can start coming down through here and seeing where the contacts at what lines contain the contacts that CR1 controls. So it says we have one in what? Line 2. So here's line 2. I follow it over, and I see a what? CR1. It says I have one in line 3. I find line 3. I start following it over. By the way, to get a line number, it does not have to come to L2. Any horizontal line gets a line number, whether it's connected to L2 or connected to L1, right? You understand? So here's a horizontal line, so it gets a what? It gets a line number. Line numbers go on the left-hand side of L1. So that's line 2. It says I've got one in line 3. So there's line 3, and it says I got one in what they're calling line 4, even though I've never seen this before. There's line 4. This one has a contact in line 8, so I find line 8, and there it is. It says it's got a contact in line 10. I find line 10, and there it is. This one says it has a contact in line 7. Let me change colors so we don't get. This says it's got a contact in line 7. Here's line 7. There it is. Says it has a contact in line 9. There it is. Says it has a contact in line 11. Where's the contacts for M1 and M2? It's a relay. So control circuits are made out of two, basically, most control circuits. Sometimes on very small applications, we can run loads inside the control circuit. A perfect example is a solenoid, right? You understand that. Actually run what we're trying to learn. So what we do is we come over here, and normally what we do is we have two circuits. We have a control circuit, and then we have a power circuit. So what I'm doing is I'm looking at a contact right here. I don't know what it was, but it's got a name. And then I come over here and I got a motor starter, which they give a name. Here they're calling it M something, but they have different names. And then over here I've got an overload. This is the control circuit. This is the low voltage circuit. This is the circuit that it's safe to get into, right over here. Okay, over here I'm running a motor. I'm running a three-phase motor that requires 660 volts AC. Well, what this guy here, it's got contacts. The contacts, we don't care if it's DC, we don't care if it's AC. So what I do over here in the power circuit, I've got contacts that's being controlled by M. They're not in the control circuit. Where are they at? They're in the power circuit. Every relay has control circuit, has contacts. If the contacts are not in the control circuit, then they got to be in the what? Got to be in the power circuit. The power circuit is a completely different diagram. You can go out and take the cover off your HVAC system, and you'll see you got two diagrams up there. You got a control diagram, then you got a power diagram, right, to run these 240 motors. So the control circuit inside your HVAC system usually runs off 26 volts. So your thermostat runs off what? Does it run off 240 or 120? No, it runs off 26 volts as part of the control circuit. So that's why you can take that cover, you can pull your thermostat off, you can touch the wires. Odds are you're not going to feel anything because it's only what? 26 volts. You get out there in your relay, and you get across that relay that's running your compressor, and it's got 240 volts. If you get across that, we'll be talking about you probably in the past tense, right? You understand that? because it'll kill you because it's a high voltage, right? You understand that? So control circuits are made out of usually made out of two circuits. And what's these little hooks? What's that the symbol for? Not the overload. These are, well, we need to make sure we understand. These are the overload sensors. So technically you're right, but you need to understand. These are the overload contacts. So here's M1. I didn't put the 1 out there. I don't see any contact. There's nothing out here on the right that says it has a contact, but it has no contacts in the control circuit. The contact, if you see a relay that has no contacts in the control circuit, why would I put a relay in there? Just to look good, right? Would I do that? No, the relay is in there to control contacts. If you don't see the contacts in the control circuit, then you need to look at the what? Power circuit. That makes sense. Everybody understand that now? So these are two motor starters. I don't see any numbers over here. So that means there's no contacts in the what? In the control circuit. So where do the contacts have to be? In the power circuit. Everybody understand that? And of course, what we do here, let's see. Underline means what? So this thing says it has a contact in line 12. Now we know it's got more than one contact because it's a motor starter. It says it has a contact, but what kind of contact are we looking for? Got an underline on it. So guys, we can't keep going back and repeating all this stuff all semester long. So you need to read your book. You need to be ready for this, right? You understand that? So here's this says it has a contact in line 8. So here's line 8, and there's a symbol. This has a bar above it. It says it has something in line 12. It's M2. I look at line 12. So what's the difference between the contact in line 8 and the contact in line 12? This is a normally closed. So an underline says I'm looking for a normally closed contact. If it's not underlined, it means I'm looking for a what? A normally open in that room, in that line, excuse me. Everybody understand? These are what we call manufacturer number. No, I'm sorry. These are what we call wire numbers or conductor numbers. These and why did we say they use these for? Well, these are what the technicians actually look for when they're hooking them up, like a car. The wires inside a car is not big enough. But if you ever look at the wires in a car, they're all different what? Starts with a C. Colors. So that's the way they identify wires in a car, by colors. They don't put line numbers on them. Inside industrial, what we do is we usually don't go to probably the only place you're going to run into colored wires in color jacket wires in control circuits if it comes in a cable. Usually cables have different color wires. If I run individual wires, what you're going to find out, normally they're all the same color in control circuits, not in your house. Your house, we run different colors, right? How many colors do we use? Anybody know? What are they? Well, it's like one of them is no jacket at all, right? White, we got green, we got white, black, red, green, right? Sometimes the green has a yellow stripe on it, and then you have no color at all, which is usually what the ground is. Has no jacket on it. So what we do in industry on these wires, so in industry usually they run all the same colors. If you ever looked in a control box, it's all the same colors. Well, how do we identify the wires? Well, we put wire numbers on them. And we usually put them on the terminal. We don't put them on the wire. on the wire jacket, we usually put them right where the terminal goes in, where the wire connects to a terminal. So wires, and somebody's going to make this mistake, they're going to number every wire. Any wire that has a common connection gets the same number. We start in the upper left-hand side. Here we're starting with 1, but it don't have to start with 1. It depends on where you're at, right? You understand? Start on the upper left-hand side. So this would be wire 1, this would be wire 2, this would be wire 3. As soon as I identify L1, what I'll do is I'll come all the way down and identify everything that connects to L1 as whatever number I assigned it. Then I start moving across. 1, 2, 3. As soon as I assign this wire number here, I'll come down L2, and everything that connects to L2 gets the same number. Y'all understand why? So now I know no matter where I'm in my control system, if I find a terminal that's got a 1 on it, and I find a terminal that's got a 3 on it, I measure that, and it'll be I'm measuring across L1 and L2. Why don't this get a number? Because it's electrically the same, right? You understand that? Everybody understand that? So it goes 1, 2, 3, 1, 4, 3, 1, 5, 3. So notice we start incrementing the numbers when we get into these inside wires, right? Why is this wire and this wire don't get the same number? Why don't this wire right here and this wire right here have the same number? It's separated by a switch, right? There's something in between. The line actually breaks. So if you're looking at a car, we got a bunch of plugs on the car, right? These Molex connectors. If you ever look, they change colors between what? This side and that side. Because they do what? They go through something that you can disconnect, right? You understand that? 1, 2, 3, 1, 4, 5, 1, 5, 3. Why don't this have a number? Yeah, it technically does, but it's still what? It's still going to be 5, yeah. And this right here would still be what? 1. So we start in the upper left-hand corner, depending on what your company does, depending on what sheet you're on. I'll show y'all a diagram of a U.S. Steel diagram, and I think it starts with, I don't forgot what it does. They start, I think, with the page number, but the last one would be 1, right? Does that make sense? These are we're going to use. We're not going to do wire numbers because our wires are so short. But when we connect up our circuits, we are going to assign manufacturer numbers. So manufacturer numbers. These are just numbers that's on the device itself that indicates where the numbers are located as far as we can make connections to them. And also, oh, I need to bring my wheel on that one. This is something that don't exist. There's a little control relay, and I'll pass it around. Now, what's nice about these is they actually come over to the side, on the right-hand side, and they give you the manufacturer numbers. But if you look at the top of that thing, at the very top of the plastic, you'll see that there's the wire numbers over there that the manufacturer gave us. Everybody okay? So this is CR. So manufacturer said this is line, this is 2, this is 10. Then this contact would be between what? 1 and 3. This contact would be between 6 and 7. And this contact would be between 11 and 9 on that. Now, what gets people problems in this is all your manufacturer's numbers are going to start with the number 1. So what happens in this class is people says, well, you need to connect that to number one, and what will they do? They'll connect it to the first number one they see, even though it's not what. It's not the number one on the component that it needs to go to. So we'll assign line numbers. So the first thing we'll do on every diagram is you'll assign what? You'll assign line numbers, you'll assign numerical cross-reference numbers, and then you'll assign manufacturer numbers. And once you got the manufacturer numbers hooked up, assigned, it's a lot easier to hook up the circuit, and it's a lot easier for me to see if the circuit's hooked up right. Everybody understand that? So we will be assigning manufacturer numbers. Sometimes so if we put a dashed line between devices, it means they are operated together. They're on the same operator. The problem is when we draw the logic, sometimes we end up with parts that are mechanically, devices that are mechanically connected together, but they're in different line numbers. So what happens is if I try to, this light comes on all the time, right? So I don't have a control device. So what they do is they put these little houses, one of them's upside down and one of them's right side up. Then they put a number in it and they say these two devices right here are mechanically connected. But if I tried to do that, it would look like all of them was mechanically connected, right? You understand? So they put these little things, and then inside the box, they put the line number of the device that it's connected to, right? Understand? And then down here, so this has got a 5 in it. So that means I'm looking for something in line 5, and this has a 1 for it, so we're looking for something in line 1. Everybody okay? So where we at in the book, y'all find this in the book, so y'all can get a better picture of it than me. You can make notes in the book, but you can't make notes on my slides, right? You understand that? So let's find this in the book, and y'all tell me what page it's on. I think my chapter numbers are a little different. What's that? And they're labeling these solenoids for you right now, but eventually that's going to leave, right? So this is a symbol for a solenoid. This is a symbol for a resistor, but it's actually the resistor of a heater, right? Understand? So all these devices don't pull enough power that we can actually control them, and they run at the same voltage as the control circuit. So I'm not saying you can't find any additional loads besides light bulbs and relays in the control circuit. It's just they have to be rated for the same voltage, right? You understand that? And they're not going to draw a lot of power. This is sort of true. A control circuit is composed of 3 different sections. They say we have a signal section, which would be from L1, is what they're calling signal. The decision section will be how we connect our control devices, and then they have the action section, which would actually be the load. Everybody understand that? We okay? Yes, no? So here's our first logic, and they're doing push buttons, which is the way our lab is going to work. Contacts, 2 or more contacts wired in series. We call that a logic AND. Now, push buttons, you've got to also realize that these could be contacts controlled by something else. So these up here could be relays, they could be push buttons. So let's do it this way. I'm going to come over here and put a push button right here. And over here, I'm going to draw a relay, and I'm going to call this A, and I'm going to call this A. And then I'll put another circuit, and I'll call this what? B, and I'll call this B, C, and D. So AND basically says what you're saying. So push button 1, PB1, and PB2 have to be closed before the rung is true. which means the solenoid is going to, what does the solenoid do for us? Linear motion. Now, we run into these things all over the place. You got several of them in your house, right? So this is a logic AND, normally open contacts that are in series with each other. And basically the expression for this is all. And here we say all push buttons have to do what? Oops. Energizer. Oops. I'll spell solenoid correct in a minute. So this is called a logic AND. Always, this is what we refer to as relay logic. So just about every control circuit is going to have some type of logic involved. To get an AND, we got to have at least how many contacts? 2. How many can we have? As many as you need. A lot of people say as many as I want, but as many as you need. Everybody okay? Yes or no? I know we have our first test coming up next week, right? This is a logic OR. Our logic OR are contacts connected in parallel. Control devices connected in parallel. Here they're using push buttons, but down below they got a temperature switch. These could be contact connected in parallel. In fact, on the test, they're going to be that way. And the AND does not have to be over here. And the OR does not have to be over here. I could come over here and I could do this. Right, you understand? And this would still be an OR. So contacts, whether they're push buttons, whether they're sensors that are connected, normally open. Now, what we're going to deal with first is normally open contacts. So these have to be normally open. So normally open contacts, control devices that are connected in series, you got to have at least 2, but you could have many, right? They're going to be in the same line. This is what we call a AND. Control devices connected in parallel. Of course, this won't do anything because I didn't put a contact right there. We call this an OR. Any. If we use the term any. If any of these contacts, if any of these devices are closed, then the output would be true. Now, I don't mean it's going to energize the load. It means that will be true, but it might feed another logic. We can definitely combine logic. Everybody understand that? We okay? So we got to have at least 2 contacts to get an OR, but we can have a lot to get an OR, right? As many as we need. Everybody understand that? Yes? We can combine logic. So these 2 right here are wired, what logic? Yeah, and. And then the AND feeds a what? OR. That's not a K. I just didn't write it. So you'll see some complex logic formed in there. We had a programmable controller called a GE Series 1. It was one of the first, it was the first little microcontroller we got. And this is the way you entered programs. You didn't draw contacts. You entered start rung, this, and with this, or with that. So you had to type, you enter that stuff in there. I wish we had one around here. I think we do somewhere. I need to fire it up and see if it still works. That was the first microcontroller we have. Because everything was done at the PLCs at the time used a dedicated programmer. These things were huge. Now what we do is we use a computer that runs an application instead of having a dedicated programmer, and then we connect to the PLC. This is what we call a NOT. A single normally closed contact would be a NOT. So that's a NOT. And we're going to have it go into a load. This is not a NOT. So this is a NOT. This is some other logic. So a single normally closed contact. Now, when we get into NOTs, NANDs, and NORs, so ANDs and ORs are what's required to cause the output to be true. NOTs, NANDs, or NORs are what's required to cause its output to be false. So right now, this output is true until I press the button, and the output goes what? Goes false. Everybody understand that? Yes or no? A single normally closed contact is what we call NOT. In digital, we give it two names. We call it a NOT logic, but we call the circuit an inverter. Everybody okay? So we got ANDs, ORs. We just picked up a NOT. What page is this on in the book? 26. 126. Then what we got normally closed contacts in series. So this right here is an AND. All these contacts have to be closed before the output goes true. This right here is so up here I use the word what? All. Down here I'm going to say any. If any of these contacts close, if any of these contacts open, then the output goes false. If you use the term any, then this is either going to be a or a NOR. Now this is what gets people, so they learn that one, and then they're going to call this a what? An AND. Somebody in the class is going to call that an AND because it's contacts in series. Your AND is what's required to cause this output to go true. A NAND and NORs and NOTs, the output goes false, right? You understand that? So at the top, I'll say all. If all those contacts are closed, then its output goes true, which means it'll move, the signal will move on. Here we're hooking directly to a load. Down here, if any of these contacts right here open, then the rung will go false. So NOTs, NANDs, and NORs cause the rung to go false. ands and ors cause the rung to go, output to go true. So I come back here. All these push buttons have to be closed to cause this to go what? True. Now, of course, here we're going to energize the solenoid, but what we're trying to do is to get it true here, because what could happen is we could come over here and have what? We could have this situation right here. So just because these two right here are true, doesn't mean that magnetic motor starter is going to energize, right? So on this one, this has the pressure switch and the float switch have to be closed, right? And then push button 1 or the foot switch has to be closed. So you can't say the load is going to be energized just because the logic does what it's supposed to do, because that will feed something else, right? You understand? So this one, the output starts off false, and devices make it true. On the NOR, the output starts off true, and the devices make it go false, right? Does that make sense what we're saying? So if I use the term any, it's going to either be a what? It's going to be either or it's going to be a NOR. If I use the term all, it means it's going to either be an and or it's going to be a NAND. I don't know how else to teach it, guys. Where's the, I'm missing a slide. I know it's in your book. And this is what we're talking about. So we can't say the output's going to go true just because this output is true. We'll call this ABC. So this output starts off true. So this can't be an AND. This can't be an AND. This cannot be an OR. So the output starts off is what we'll say is true. So how would I make it go false? All these contacts have to open, right? So if I say all, it's going to either be an AND or a NAND. So this is a NAND. What page is that in your book? Somehow I've lost that. The NAND? 26. I don't have slides. I don't know what's happened to it. Somehow I got deleted. So that's 5 basics. That's it. All digital logic is made up of these 5 basic logics. What are they? And, or, and, or, not. So a single normally open contact, what logic does that perform? These guys perform no logic. They're just, in digital, we call them buffers. They're in there for a reason, but they don't do logic, right? You understand that? So what logic is this over here? We actually got another logic in here. What logic is this? Single normally closed contact. What? Yeah, there's a not. But somebody over here is going to see this, and they're going to say that's a knot. It's not a knot because there's two of them now, right? Exclusive ors and exclusive nors. Is this covered in the book? Really? So y'all need to make notes on this. This is probably another one of the most widely used circuits and controls. Exclusive ORs and inclusive NOR circuits consist of 4 contacts controlled by the same 2 inputs. I need to put 2. Exclusive ORs create a true rung when the control devices are in a different state. Exclusive NOR creates a true rung when the control devices are in the same state. Now logic, and we'll go over this. So what we're doing, a lot of our control circuits are being replaced by these computers. We call them programmable logic controllers. Now, the advantage we have over this, of course, it replaces a bunch of relays. The only time we actually use relays is if they have to change voltage levels or control a lot of power. And another thing is they're programmable. They're computers. So normally, if I used to when the car manufacturers was getting ready to make a new model car, they had 2 lines. They had one that was running this model, and they had the other one that they was rewiring to run next year's model. And it would take a long time to do that because they had to rewire the whole circuit. What we run into now is all the control is in a computer. So when they change things now, they don't have to go out there and rewire a circuit. They just do what? They just change the program. Okay. So what we do is we do all this logic programming in these things. So we do the same thing. So instead of me having contacts and series, I draw them in a program, right? I'll show you all the program later on to see once you learn motor controls. So the original language that we used to program PLCs was what they call ladder language, because PLCs originally was put in there to replace relay logic, or most of it, not all of it. We still got to have relays, right? You understand that, because PLCs can't control high power devices. So now we take our push buttons and we hook them up to the input of the PLC. Then we write a program, then we control outputs. So what we're saying is that once you learn this, but what happened was all the people that got into this did not come up through motor controls. They come up through digital. They came up through Pascal languages, text languages. They came up through computer science, where they did all this flow charting and stuff. But what they've done over time in the PLC, originally the only language they came out with was ladder. But now they support several languages. So that means no matter what you came up with, odds are through the engineering trade, except for mechanical engineering, through the control trade or came up through there, you would be able to program a PLC in a language that you understood. Right? So originally when the internet came out and they started doing these websites, the only way you could make a website was in English. So that means if you were in a different country and you got on the internet, you had to do what? You had to learn our language. Because the code we'll look at that they used to represent characters was an American code. It was called American Standard Code for Information Interchange. And it's called ASCII. Well, it's nothing but represents the English language. Well, eventually they came out with a new code called Unicode, which is a 16-bit. It's actually more than that, but normally they use 16 bits. which gives it 65,536 characters now. So now you can get on a website and it could be in what? It could be in English, but it could also be in what? It could be in Japanese, it could be in Chinese, because now they developed that. Well, what they did is they came up with a programming language called a function block diagram, which basically uses, we program in symbols. So the symbols for an and, we'll show y'all the American symbol would be this, looks like a D. And then you come in and you bring in the inputs on this side, and you bring one output. And this is the symbol for a logic AND. The symbol for a logic OR is we put a curve on this side, and then we bring down this. We bring our inputs into this side. I'm going to do 3, even though this is 2. And then I would come out on one side, and this is the OR. So now we can program PLCs using logic symbols. Instead of all the relays, I just pull a symbol, I drop a symbol down. But they use ISO symbols and not US symbols. So if I was going to program this in a PLC, I would come over here and I'd start off with and then I'd bring in a pressure switch, then I'd bring in a flow switch, then I'd take this off, and then this would feed into an OR. And that's the way we would program it. So an exclusive OR or inclusive NOR, this is probably another most widely used circuit. And what this does is it always only uses two inputs. And what these are our comparators. So what this will tell us if the two inputs are in the same state or if they're in different states. Everybody follow me so far? Have I lost anybody? So what have I got? 2 push buttons which are controlling 2 relays called A and B. And then here's my exclusive OR. And exclusive OR has a symbol like this. You can only have 2 inputs. No more, no less. And then 1 output. Now this, we got 2 outputs. We got this guy we'll look at in a minute. So this would be a symbol for a NAND. Let me get back to this. This is a symbol for, this is a, what is this? Oh, I got it out there. What is this? If any input opens, it'll cause the run to go fault. So this is a NOR. And what we do on this is we put a bubble on the output. Now, here on digital, would say any high will give me a low. Here we're using truths and faults. So see, I heard somebody saying and because they saw these guys in series, and that's the biggest thing you got to learn, guys, is just because you see contacts in series, and somebody's going to do that in this class. I wish they didn't, but they learn the and they say, okay, contacts in series is an and. Then anytime they see something in series, they want to call it a what? An and. But that's not true. An and is normally open contacts in series. These are contacts in series, and the problem is somebody's going to call it an and because they'll just switch it over. But here I say, if any of these contacts open, the run goes false. If I use the term any, it's going to either be a what? It's going to be an or it's going to be a NOR. So your NOTs, your NORs, and your NANDs, the output starts off true. and then the logic makes it false, right? You understand? On an and an or, the rung starts off, the output starts off false, and your input makes it true. So if you sit there and you look and you see that the output of this is a false, it cannot be an and, it cannot be an or. It's either got to be a not, an and, or an or. So that's the way we would draw that. Now notice we got, so this says any high on the input. So in digital we use highs and lows. Any high would give me a low. And this is a touch, by the way. So they use a bubble to indicate the output is false when the inputs are true, right? You understand? And they don't use the bubble for when the output is, when the inputs are true, the rung would be true. That makes sense? Well, on exclusive NOR, we only have two inputs, period. There's no such thing as a three-input exclusive OR and exclusive NOR. So notice here it don't have a bubble on the output. So if I saw this one right here, this would be an exclusive NOR. But usually we abbreviate X. NOR, Rich. Rich. So notice when none of these buttons, when neither one of these buttons are pressed, would the output be true or would the output be false if I don't press either one of those buttons first? How? I'm not, I said if I don't press any button. If I don't, this is what we're looking at. What happens when I'm not pressing the buttons? That's why we start off. The output would be false. Everybody understand why? So A is not energized, so my signal would be sitting right there. Down here, A is not energized, so my signal would be sitting right there. So it would start off false. Okay, so I come over here, I'm going to press the A button. So this is closes. This relay energizes. This contact would open. This contact right here would close. So would the output be true or would it be false? It would be true. Oops. I'm having a problem today, guys. So what this does on exclusive OR, it shows us what happens if the inputs are not equal. So it says the output would be true if the inputs are not equal. Because A is true and B is false, right? It's gonna be one of those days. So let's come up here and let's press B. Press this button. This relay energizes. It's going to close this one, but it's going to open that one. Is the output going to be true or false? It's going to be true. Because they're not equal to each other. So let's press both of them. I'm going to press this one, this one. It's going to cause this contact to open. I'm going to cause this contact to close. It's going to cause this contact to close and this contact to open. So the output's going to be false. So this symbol is kind of backwards of what we see it. This tells us that when the two inputs are equal, the rung will be false. When the two inputs are not equal, the rung will be true. So that shows you what it is when they're not equal. We had over on the manufacturing line, we were programming an HMI panel, and it's got a button, it's got a switch on it that you switch it between manual and automatic. Your manual, you could cycle it one time. On automatic, it just runs. When we put the HMI panel up there, we wanted to put a simulated switch that does the same thing. But what we wanted to do was have them in the same position, right? You understand? If we put both of them in auto, it would be an auto. If we put both of them in manual, it would be. And of course, this is the one we use, one of these guys right here. It works pretty good. So this is an exclusive NOR. This would be the symbol. This says if the two inputs are equal, the rung will be false. We went to training Siemens when we was trying to get our capability to do our level 1 certification, and we went to Motlow Community College up in Tennessee, and their actual manufacturing classes are inside the big Bridgestone power plant up there. So they actually gave them that section to do that. And these guys are up there talking about these, and they says, can anybody draw an exclusive NOR? So it's on their Siemens. Of course, I went, I can do it. So here, they're equal. Both of them's open. So both of them's open. Would the rung be true or false? So this says the rung is false if they're not equal. Here they are equal, so the rung starts off what? True. I'm going to come here and close this button right here. When I close the button right there, that's A. This contact is going to close. This contact is going to open. This contact right here is going to close. So what's going to happen? Rung's going to what? Go false. Come over and close B. Going to energize this relay. Of course, I should put numbers over here, right? Going to energize this guy. This guy right here is going to open. This guy right here is going to close. They're still not equal, so the rung's still going to be what? False. So we should expect the next one to go true. This says if they're not equal, it's going to go false. So we should expect when I come over and close both of them, it should go true. I'm going to close this one and close this one. This contact's going to open, this contact's going to open, this contact's going to close, this contact's going to close, and the rung goes true. So what we do with exclusive ORs and exclusive NORs is we have the ability to see if two inputs are the same or two inputs are different. So these are errors. PLCs realize that this is very, very important. So they've added additional instructions, but this would be for doing what we call relay logic. So relays, basically, we can do the 5 basic gates, right? You understand that? And then these advanced circuits. So there's 7 logic operations that we can perform with relay logic. PLCs are computers. they'll do all of them. I mean, they'll do math. They'll do compares. They do all kind of neat stuff. But instead of only working with two, the limitation we have with here is that we can only deal with two. We can see if two inputs are either the same or different. Which limits us a lot. But PLCs are computers. I mean, we can do what they call uh, double words to be 64 bits or individual digits. Inputs were either all the same or all different with PLCs. So PLCs expand that because it's a computer. So these guys can do a lot of things that we can't do with relays. So relays can't do math, right? You understand that? They can't do trig, which would be math. But a PLC is a computer, and that's another big thing, advantage of a computer, is that we get access to not only the relay logic, but we also get access to all the different things that a computer can use. Yeah, you can set this thing up with a web browser on it, so you can access it in a web page, which is pretty neat because it's a computer. So what we have here are these two guys are connected in what? But logic, I'm sorry. What logic? Okay, does it start off true, or is it the position they're drawn, is their output true or is their output false? Okay, so if it starts off true, then it's going to be a not, a NAND, or an OR. If it starts off false, it's going to be an AND or OR. So that's the first thing you're looking at. If it's true, if it starts off true, if the output starts off true, it cannot be an AND and it cannot be an OR. So I'm going to look at this and I'm going to say, okay, both of these, all of them have to, as soon as I say all of these have to open to cause the output to go false. So if I say all, it's either going to be an or it's going to be it's either going to be an and or it's going to be a NAND, right? So this is a what? This is an and. This starts off true, so it can't be an and, right? You understand that? It's either got to be a what? Oops. It's got to be a NAND or an OR. So I say, okay, if any of these guys are true, then the output will go false. I mean, if any of these outputs are true, the output will go false. So if I say start off with any, this right here is a NOR. Well, what's this logic? Here the output of this one starts off false. So this is going to be either an AND or it's going to be an OR. If any of these close, the output would go true, right? So if I say any, this is going to be an OR. And then, of course, this is a not. It's not okay, Rich. It's an OR. So if you look at devices, and if their output starts off false, it's going to be a what? It's either going to be an AND or OR. If they start off true, it's either going to be a NAND, a NOT, or an OR. The NOR is real easy. The NOT's real easy. It's going to be what? Just a single normally closed contact coupler. Right? I know. I saw that. Thank you. Okay, everybody okay? Sure. Of course, these PowerPoints are available online. They better be. If they're not, you need to let me know. Okay, I'll make sure it's up there. Thank you. the output. I mean, we can't say the rung gets energized because we combine logic all the time. So when we're talking about true and false, we're talking about what's going on out right there. Does the signal get true? Does the signal get through, or the signal not get through? And the signal's got to flow all the way from L1 all the way to the load, right? You understand, to L2. So if the output, so here, the output starts off what? True. The signal gets through these. So if the output starts off true, it's got to be a what? It's got to be a NAND, a NOR, or a NOT. If the output starts off false, it's going to be a what? It's going to be an AND or OR. These are all either normally open or normally closed. When you start seeing normally open and normally closed in right here, then something's got to click. This is not an AND, this is not an OR, this is not an AND, this is not an OR, right? You understand that? Because we have two different contacts, and this is where your exclusive logic functions are come into play. So this one, and that's what you was looking at a while ago. This one starts off false. Right? This one starts off false. This one starts off true. And that's what the little thing says. Okay, guys, y'all take a 2-minute break. 9:55. If you came in late, you need to let me know. I know you already. Maurice, I know you. In Leith, right? You was absent last class. You was absent last class. And you've been here every other class. No, you've only been absent one class. So that was last class. So I have you absent there. And then this class right here, I have you present. And then this class right here, I have you present. Yeah. I got you here every day, but last week. So you need to mark these out, like I have up here. This would be angle. This could be it. This is also true. And I didn't, when I started making corrections, I didn't have this one. I go ahead and say, up here, everything is like that. Yeah, so this was the truth table. We had to show how the output responds to changes. It's called a truth table. Sometimes they call it a function table. A lot of times it's easier to see a certain operation table than actually try to figure out the setup. So anytime it's got zero, or zero fall, and then one true. That should be right. Well, the problem is that scroll on I'm there, and now what's happening is over here I got three inputs. They would be A, B, C, but in my truth table I only show two inputs. A, B. So that means in the output, the X would be the actual output. Watch. But see, the problem is that, and I don't have enough space because if I right now two inputs, I have four rows and columns. If I add another one, it would double it up to eight. Well, if I try to add another row, then the thing would be too long to get on the same page. So what I've done is I've marked out in the and I marked out this contact on the right. On the or I marked out the whole thing in the bottom. This one I marked out like this. NAND, right? I mark out the bottom. I mark out the contact here. And I'm calling the contacts AD, 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 AD. And then they're over here in Tuesday. Make sense? So, now the exclusive OR and exclusive OR is okay because they always have to undoubtedly whoever modified it will show you that you gotta have at least two, but you can have a lot of them. The problem is if the truth table did not match the first. So that top one says all input. The top one says the inputs to false, output will be true, if the input is true, output will be false. That's not right. But the second one says all inputs have to be true for the output to be true. But this says any input has to be true for the output. So if I've got a one anywhere over here, I get a one back. This says all inputs have to be true for the output to go false. So these start off what? They start off true, right? Like this. So these are the true tables for those different games, those different logic. I don't have the exclusive OR. You should say exclusive OR, exclusive OR. You got two ones in there, right? You don't need to make that correction for me because the truth table does not match the perfect. I'll come back and get time to mark this out. Because like I said, if I try to put the truth table in here, so every time you add the number of rows doubles. So if I add one more C, then I have 8 rows. If I added a D, then I have 16 rows. So truth table runs in power. So yeah, so y'all like that. We pretty study diagram we're using in terms of all contact to get the output of all. true, he starts off false and then you make it. And the Lord is not. Now, starts off true, you make it false. Starts off true, it makes it logic. The other one is y'all get that? Everybody got one of these? This is actually print provided to by U.S. Steel and you call it of course. This was number 4 galvanized. One section, number 4 galvanized until they convert to yes. I couldn't pay. I should get that out. I can see. See if everything's true. And we just went over the standard draw. So here's line numbers. They're all on the left. Every horizontal line. So notice this don't have a line number because it lines up. So if I was to, it lines up, keep going. So if I follow this, here we go. Go through it. So these two guys right here are lined up. So since they're in line, they can this one line. You notice they're starting their line diagram. 137. On page 137. We start. Then the line numbers go. Same page number. 1, 2, 3, 4, 5, 6, 7, 8, 5 talked about, right? Okay. These are relays. These are the names. We're going to use very simple names like CR. They all got every relay. It's got to have. This is a comment over here that tells us how to average. 5B1DB, that's number 5 drive. Dynamic braking context. Then it says I have lines. Some of them we can't get to because they're on the page. The way this starts out, it puts page numbers in parentheses. So this guy's got a contact over on page 2. I got to turn over there to find it. These guys, I don't know. But it says it's got a contact in line 2. 5. So I come over here to line 2, start with code, and I'm looking for same name. 5B1D1, 5B1DD. There's that contact. And it says I've got a contact line 7 down here somewhere. But that's not even. This one says I'm looking for a normally open I'm looking for a normally closed contact on page number on 137. So I gotta find that page. Then I do what? This is being what? If we got one. That's part of the Okay. How do you know it's normally closed? Because it's underlined. If it's not underlined, open line. If it is open, it is underlined. Close line. So if it's not underlined, we're only open contact at that time. If it is underlined, we'll be close contact. Change it off draw like that. If I can't get it off draw, I have to do that. What are these right here? Now notice, so everything under C, keep on line. Everything on D, also you cross reference. And everything out here C. 137.012. Starts off with 1. They don't put in 1370. We don't see any more down here. We also have, have the same wiring, right? Over here, when we get to 137.13, we don't see anything down here. We all have. So these right here, I don't see any wire down right here. All of them are connected together. Every one of these has but every time I go through something, I get another wire, right? So this is, are we okay? This is a perfect example of actually industry standard wiring. It follows the exact to see on thing they don't show. So being with the wire numbers, letter numbers, line numbers, these shows us location, contact, within the diagram. So we have 3 types of relays we're running into. This might be a little different on where you work at. Always know what it means that every place I do work have different terminology. So what we're going to see is we got 3 categories of relays. Called a control relay. Here we're going to make it easy though. Real life, they're not called y'all. And then we have another relay. These guys all contact. So these guys will not have any contact outside of the door. You have no contact in the power source. As soon as I do the contact in the power source, then it goes what we call a contact or a motor. These house contact in the power source. Contact key. These are usually strapped to the side. Low contact side. That one don't. It's got an extra set of contacts. So this guy here has 4 power contacts, and like I said, I got my camera on my. Put the camera on my computer. So this has got 4 sets of power contacts on it. Strapped onto the side over here. These are the, and they're operating. By the way, most of these relays have what's called, I think it's called push and fed. These are actually on fire. And you can check the circuit out. Guys are very dangerous, right? And we build all this safety control, and then they give you a name override knowledge. Make sure you understand what's going on. So when you press these override, see the guy that's talking on that. The guy went in wrong direction. He was in talking on the blast furnace. I'm ready for the blast furnace before they tore it down. With what they call a positive pressure furnace. So it actually had hoppers in the top and had conveyor belts that was grain. Zero up, drop it in, and they would open top hopper over, and then they hose bottom hopper to drop it into the furnace. And they were working on one hopper over, bottom hopper over, they locked it out, they did everything they supposed to do. What did they do? They didn't lock up the top. So they got down in the relay house, check it out. He wanted to see the actual extender valve, just to extend. The guy pushed in the wrong one, the top hopper door came down, cut the guy in two. So you got to be really, really careful. You use these manual override to understand what's going to happen. We had a galvanized strip that they were putting zinc coating on, ran it like 7 feet in. And it had what they do is come in coil, line. They lay it across the top, and when this coil runs out, they would stop it and cut it and overlap them, weld them together. But they clamped it down on the side. I was in there, we was checking on something, I was pushing in a relay, I was in the side clamp. The line was running wide open. They were running a narrow strip. They didn't grab the line. They couldn't grab the line, of course. That was my fault. I looked down. No, yeah, this is probably we've got these operators that strap something on the side. So this has one set of auxiliary contacts. So auxiliary contacts are not intended to run power section. They're intended to run in the control section. Now this one has 4 sets of power contacts on it. So a lot of times power contacts like it with auxiliary. But it could handle a lot of one. It could handle a lot of one. You can actually see the overload. So that's a magnetic motor starter. That's what we call a motor starter. How manual.
contactor. So, in fact, most of the time you'll look at the contact that put it on the plate physically now, so they don't make a motor starter. Make a motor starter, they make contact, and then they mount both of them on the plate together, and they just wire them. Most magnetic motor starters I've seen like that. So three types of relays, right? Contact is relay, either relays that will have contacts in the power system. They might have auxiliary contacts in the control system. And then a motor starter. The motor starter is contact with that. Yeah. Most people just call them motor starters. We do have two motor starters. We have a manual motor, which has push button functionality, and then a magnetic motor starter. But this is basically what this contact is. What is overload do for it? Overload. So the problem we have, this is about the third time we've talked about this, is that a motor pulls between 6 to 8 times the current when it starts. Your fuses have to be rated, your overcurrent protection device has to be rated to allow them to start. But what if the motor don't start? Well, the overload current protection devices are not going to do anything for you, they're just going to let them from up. Right? So what the overload does, it allows current to flow over a short high current. It's looking for overcurrent over time. So if the motor don't start, overload will kick the motor out, or it has or if it stalls, right? So just about every motor, except those tiny anything I think it's quarter horsepower has to have an overload. A lot of your all as far as I know, all those on your house, these are kind of dangerous to talk about, which means they'll kick the motor out, and as they cool down, they'll get back on. Those don't kick out the actual control. So they're not in there to protect you. Auxiliary contacts are added to the circuit with push button memory. That's not exactly. An auxiliary contact is a contact that stays where? In the control circuit. A control relay, all of its contacts. So this is what we call a memory circuit. It's also called a three-wire circuit. So if I gave wire numbers, we thought it was good, might have to name. Well, let's start. This would be wire 1, this would be wire 2. This is the same way. This would be wire 3. So there's 3 wire numbers between L1 and so a lot of people call it 3 wire. Some people call it a memory circuit. They would call it a ceiling or a start circuit. So we have here, this is a knob. So this output starts off true. This is a 4, even though this is not touching. I draw mine up. Look at it, you draw them really close together. If you look real close, you'll see there is an air gap up there. So this is an OR. And this is a magnetic motor. and your loads are gonna have names, right? Here they're gonna put the name on the inside, the judge, steel screen, if they had names for you. Look above it. But here we're gonna call loader sorter, so we name CR, CR2, CR3. And in real life, they're gonna run out of CR back. And they like to try to give it a name, basically what we made up. So I'll call that out. Number one drive with dynamic range relay. I need to flush by looking at mine right so the names are. So how does this work? We start off, this is true, this right here, false, right? So my signal is hit. Signal signal. Now this is the magnetic motor starter with overlay, so I know this guy's gotta have what? He's gotta have contacts and power circuit. Especially as soon as you see that. So I come over here, I press the push button, it's a momentary contact push button, probably 90% push button, probably 95% control or momentary contact. You got a spring there, you press them, and you say that so I press the push button, that closes this circuit, comes over here and hit in, and now in. Close this contact right here. Now we got a secondary path here. What can I do now? I go to start. This is it. And it seals in. Motor comes up and does run. Until I hit the what? Yeah, hit the knot. Do the knot, right? Press the knot. Causes the relay to drop out, and goes from contact, fall out, right? And the load this contact, everything's done. So I've added one less. I'll show you on this circuit. So we got one more contact here. Contact. So this is the guy. So what I would do is I'd add relay here. I'd go relay here to the bar and so this is the circuit. This would be an auxiliary contact. By the way, on these sensors, the manufacturer numbers are on the back, but we don't know what's what. So these things are coming with some type of issue thing that they use to throw away. Then they need to be wired to that stuff. But if you get some of those things, you need to start you like a book or something, for each function out and put those things in there. So you might have to come back and do some rewiring, right? That's the problem. So they change the circuit mode, you got to rewire. If you've lost that, and it's you and an on there, right? Trying to figure out where your normal solar contacts are, where your normal contacts are. Or you're probably going to have around these AC poles. They'll probably have a couple thousand ohms there. So you just find it. You're going to the manufacturer trying to find that where you have a book. So in the drawer up there is a book that shows you all on our device. Exactly where there's manufacturing. And it shows you how the overload is wired. Now this one you can actually see where this is nothing but a contactor on the top. And the overloads have been added. You just mounted it on the front plate. This is very, very powerful. So now we can most I've seen. Big one that I ended up with today, at 5 horsepower, like 36 road, all the things you feel. Everybody understand what auxiliary contacts? These will be on contactors, will be on overchargers. Auxiliary contacts are probably control. Okay. Carbon stop control is created by adding a dot logic stop button to a neutral circuit logic created contact. This is probably, like I said, this is probably the popular circuit out there because it allows us to push buttons instead of switches. The push buttons are nice and big. They're inside a sleeve, so you bump up against them, you're not going to actually get them. So now we can do what we start and stop things with the thumb. Unfortunately, a lot of people, even with these guys that's got the HMI panel, these push buttons are still popular because the HMI panel, these buttons are all simulated, not real, they're all touch, right? And what happens to computers? Yeah, they got issues. All it takes is just something to change a one into a. So your phone locks up every once in a while, right? So everybody knows how to reset the phone. You'll restart on the phone. You need to buy it out. Sooner or later your phone will lock up. Sooner or later. These engineers, they know how everything's supposed to work. And they put that out in the room. They do things that they never done. Even games, I do games. Because you do something good. Two-star stop stations, this is very, very popular where everybody on the local, and I've seen more than that. So what we're doing is we're setting up what logic is. Yes, is no. So we say any, by pressing any of those buttons, right? Just right here. So here we have two-star stop stations where I can stop the motor from this location. So I'm down here 50 feet away from my start station, but I'm at a spot where I need to run the motor. Then we would have a stop button there, and then we have a start button situation. I've seen this a lot. So I've seen one, I think, we had one that had like 32 e-stop buttons. And these stop buttons are just stop buttons, but those only they latch. Same circuit. It was e-stop with there's stop. 32. And they have the main contact. Two-star stop station that we use. This is pretty popular. We have one e-stop. See the e-stop there? And then we have the regular stop. Well, I can stop the top one without stopping the bottom one, or vice versa. If I hit the e-stop, it'll kill everything. You see that? Yes, sir. Here's my line numbers. Here's my cross-circuit numbers. So it says this is the motor starter. It has contact. There we go. So the only thing that has contact numbers are relays. Solenoids don't have numbers over there, and lights don't have numbers, right? Who in this class is going to assign line numbers to a crossroads light? Somebody. A class this size, guys. Somebody needs to do that. for the lab book and the textbook, you need to get a lab, if I understand. So the first two labs,
The first two labs